This program is a presentation of UCTV for educational and non-commercial use only.
Good morning, everybody, and welcome to this second Roots of Energy Efficiency event. I'm Russ Yarrow. I'm General Manager for California Corporate Affairs at Chevron, and we're delighted to be the sponsor of this event. Chevron really has a robust relationship and partnership with UC Davis. We've been collaborating with the university on advanced biofuels research for a number of years now, and we are a founding sponsor of the Energy Efficiency Center, which we're also excited to be involved in. We were honored last year, of course, to be able to endow the Chevron Chair in Energy Efficiency, and we're excited about that search starting soon, and hopefully next year at this time, the holder of the chair will be up at this podium. I promise not to make this a Chevron commercial, but I do want to let you know how important energy efficiency is to our company. I think most of you know that we sell energy efficiency in the marketplace through Chevron Energy Solutions, and our CES's COO, John Mahoney, is a participant here today, so you'll be hearing more about that company and the great work that they do. Helping to realize the full potential of energy efficiency is important to us, and we believe that the best years of energy efficiency are ahead of us. I heard Ralph Cavanagh once refer to the coming golden age of energy efficiency, and we think that's true, especially with the kind of work that UC Davis is doing. And we think it's particularly important because energy efficiency is not only helps our business, but it reduces the emissions and financial costs of energy use, which is obviously very important. And when it comes to energy efficiency, nobody has cleared a path or shown a way forward as much as California has, which is really the topic of these events that we're in the middle of right now. California is really a global leader in energy efficiency, and so we think events like this are important, not just to reflect on what California has achieved in energy efficiency, but how California and UC Davis can help lead the world to the next generation of energy efficiency. So thank you all for coming out today. Look forward to a great program, and I'll hand it over to Alan Meyer, Associate Director of the Energy Efficiency Center. Thanks.
Good morning. My name is Alan Meyer. I'm here first to introduce Jackie Pfannenstiel, who was the director of the California Energy Commission. Her bio and those of all the other speakers are in your packet, so I won't review them. But without any more introduction, then I'm going to ask Jackie to come and speak. Thank you.
Thank you, Alan. I'm honored to be here. I really appreciate it. I've left the Energy Commission at the beginning of this year and have been sort of going around dabbling in various energy matters, but primarily energy efficiency, because this is both where my passion is, and I think as we just heard, I think this is where the future is. So let me start by pointing to the obvious. We've been doing this for a long time. We in California have been doing energy efficiency for 30-some years. It started really right after the OPEC oil embargo of 73, 74, where California passed landmark legislation, the Warren-Alquist Act, which created the Energy Commission, but gave the Energy Commission the responsibility of setting mandatory building codes and efficiency standards for appliances. Big step, hard to do, but have been held to that ever since. And then in the 90s, the Public Utilities Commission began working with the utilities on programs for the utilities to invest in energy efficiency in lieu of investing in new power plants. big concept. Now we take that more or less for granted. At the time, it was an enormously important and revolutionary concept. And the way they did that is they decoupled the company's profits from their sales, so therefore they had no incentive to increase their sales. Again, something we in California take pretty much for granted, but is just now something that the rest of the country is once again debating and rather frightened of, I would say, in some ways, and yet we have a long history of it working here. Now, in '96, there was the energy, electric industry restructuring, and as part of that, to make sure we didn't lose the forward progress in energy efficiency, we captured both the public goods charge as a way of as some funding and some public interest energy research, big dollars, to continue the R&D portion. So my view is that we have 4 parts of our energy efficiency program. We have building codes, we have appliance standards, we have the utility procurement programs, and we have R&D. All 4 of them have been important and effective, and we're moving forward with them. Now, mostly I think you're going to hear today what we've accomplished and what's left to be done. Let me start by saying my view is we've accomplished enormous things. Technology improvements, which I think everybody will talk about, and I have some slides that I think others will show in more depth. But also where California is on standards tends to be where the country goes. People have asked me several times, well, gee, does it matter if California does it? If California adopts certain appliance standards, we're a big state, but we are only one state. What about the rest of the country? Experience has shown that as California adopts standards, appliance standards that require a product, an appliance, to meet a certain level of efficiency, that happens, the rest of the country then follows suit, whether they do so on a mandatory basis, which has happened, or whether the product manufacturers then discover this is a better way of manufacturing and selling. And so our products have taken over the country. I'll show this famous per capita electricity use slide, which shows one measure of success. But we also find, and I found at the Energy Commission, we're constantly in demand for what is it you do in California? Why is it that works in California? And that's just not nationally, but internationally. The refrigerator story. This is really quite impressive. You can see that from the end of World War II, this pink line shows the size of refrigerators. And since the end of World War II, refrigerators have been increasingly larger. Electricity was cheap, people had bigger homes, more disposable income, larger refrigerators. And you also see that from that time, the energy use per unit, as these refrigerators were getting larger, was continually going up. California imposed standards in the end of the 70s, beginning of the 80s, and look what started to happen. And then the federal standards, and this arrow was way off, it should be over here, and federal standards came in after that. But when you look at the efficiency of refrigerators compared with where they started, impressive story. 3 other, and here's a refrigerator based on just an index to 0, index to 100, refrigerators, but you see the same thing in central air conditioning, you see the same thing in gas furnaces. One thing this points out is these clear white arrows show California standards when they went into effect, and they keep getting updated. And then the black arrows show the national standards. So you see in all of these, California started, the national government, the Department of Energy, then picked up standards. What's happened since then? The appliance standards have saved energy, building standards have saved energy, these utility programs have saved energy. Something like 15% of our whole energy use has been, or what would have been, has been reduced. I label this utility programs and price effects because there are some things going on there that I don't think we very clearly separated. But we know that the utility investment has made an enormous difference also. So this is the per capita slide. On a per capita electricity use basis, the United States has been continually increasing since beginning of the 60s. California, during the beginning of that period, was increasing just about with the rest of the United States. But since the mid-70s, beginning of the 80s, when the standards went into effect, and when the utility programs came into effect, look what the difference has been in California. There will be continual arguments about how much of this we should take credit for and what caused all of this. I think the impact, though, is dramatic, and we have seen that. However, I would point out this isn't exactly bad news. The good news is still there. But this is Western Europe per capita electricity consumption. What you can see here is, even though theirs is increasing, as good as we think we are, there's a ways to go. There's, in fact, quite a ways to go. And this is what we need to be concentrating on, is how much farther we can go from where we have been. What can we do? Well, clearly, we need to keep upgrading our codes, our building codes, as we've been doing. We have the building codes apply to new buildings and major renovations. But what about the 93% or whatever it is of the existing building stock that was before the later building codes? We also need to reduce the costs of energy efficiency. Well, improving codes is the most effective thing. Frankly, the utility programs are really effective but expensive. Something like 10 times more expensive than getting these savings through the standards. And that's because utility programs are based on incentives and rebates and giving the money to get the program costs down. It works, but it's expensive. What we need to do is make sure those programs are giving us some long-term benefits. I'm going to talk a little bit more about this in a minute, but the fact is the other thing we need to do is change the American culture, change the Californian culture on use of energy. So in the codes and standards, clearly we need to keep up capturing the improvements. We need to make sure that we're willing to step up on efficiency standards for appliances. People have been reading, I think, in the newspaper about the television standards. Big pushback from the manufacturers about whether there should, in fact, be efficiency standards for televisions. The Energy Commission is pushing that there should be, that there can be, but there's always political ramifications every time you're moving the ball down the court. The other thing we found is that enforcement is critical. You can have the best codes and standards in the world. If they're not enforced, you've lost the opportunity. And we need to focus on existing buildings. How do we get the cost down, though? How do we make sure that the cost of investing in energy efficiency is such that people are willing and able to do that? We know that we're putting a lot of money into that, into rebates and incentives to overcome the resistance of the market to invest in these. But we have an issue here, and that's that we end up, because this is utility money, because this is customer ratepayer money that's going into these programs, we have to evaluate and verify the savings from them. That has led to a focus on more short-term impacts because they're easier to measure and evaluate. So a lot of what has gone into the utility programs has been relatively short-term in nature, hasn't really transformed the market the way we would want it to. But this is into the market transformation. Can we do this? Will Americans be willing to adopt a culture of energy efficiency? You know, we've known for years that there's this kind of negative connotation. People in this room probably don't share that because this is what we do. We know about it. But, you know, a large part of the country thinks of energy efficiency as you know, people say cold houses and warm beer. I mean, there's a negative sense there. Besides which, there's very little information. People don't really know what they're using, when they're using it, how much it costs. There's also, I think, a really shocking lack of public information out there. So what can we do? The obvious are expanding the mandates. we do that. We update those. The mandates need to be technologically feasible and cost effective, but once they meet those tests, we can continue to expand them. We need to improve the economics, and there are things going on in improving the economics. Tax incentives, economic stimulus bill, there are things that are happening to improve the economics of energy efficiency. We also need to bring in the new technologies. And it's not just the technologies, I think, that we'll hear some about today, the appliances and the lighting for the most part. There are also, for example, the new smart meters that are going in all over California. When those meters go in, we have the possibility of enormously new uses of the information then that will be collected. Not only will people be able to see what they're using, when they're using it, and how much, or how much it costs, but think about the iPhone. Did I just hear that there are like 15,000 apps for iPhones? How many apps can you think of for the information that will come from the smart meter? Ones that people don't know they need, don't think about right now. There are really enormous possibilities here. Leadership is, interestingly to me, we're starting to really see a difference. Look at what's happening in Washington. The economic stimulus bill was replete with energy efficiency opportunities. It's happening. People are seeing it. People are understanding it. California has been there for a long time. I think the rest of the country is getting there. But we need to do a lot more on educating and informing the public. Well, how well have we done? I would say that we've looked really good on several of these areas. We've made some big improvements. But as far as the attitudes and the culture, I think that that's what is wide open for us to do. I think that part of our getting together here, part of what UC Davis is able to do, and throughout California, when we have the will to do it, we need to bring the public along with us. It can't be just people in this room talking to each other about what's going on. It's a great opportunity. Thank you for your attention.
Thank you, Jackie. I'm going to talk about where we left off. This is Roots 2. That means it's the second in our series about talking about the roots of energy efficiency. And in the first Roots lectures, I began by defending the less than humble subtitle of the series. Maybe you never even noticed the subtitle, which was How California Changed the Way the World Uses Energy. But now I don't need to defend it. I need only quote President Obama in response to a question about California's energy efficiency rules for automobiles. President Obama said, consistently, California has hit the bar, and then the rest of the country has followed. So you can see that California is changing the way the United States uses energy, and I will be able to show you in the future Roots how California has changed the rest of the world's way it uses energy. I introduced the Roots lecture in October by showing a chart of electricity use during the past 30 years. You've seen this now several times, and you're going to see it some more because it has so much information in it. And in the initial Roots, I compared California's per capita electricity use to the United States, and notice how I added Texas. Jackie was more diplomatic and just left the rest of the United States. And the difference here is that I reflected on the right-hand turn that California took, just about right here. Just like the United States and Texas, we were all climbing with year-on-year growth in per capita electricity consumption. But then, around 1974, something happened. It's called an oil embargo. But California did something different. And somehow, California took what I call a right-hand turn. And since then, for over 30 years, California has been maintaining a more or less constant per capita electricity consumption. Of course, California's population has grown so that the state's total electricity use has also grown. But when you compare this to the other regions where per capita electricity use continued to grow, you can see that something different happened in California. And we know, as Jackie explained, there were many reasons to explain this difference and this right-hand turn in California. Higher electricity prices and the transformation of California's industry to less electricity-intensive activities. Those cannot be ignored, but California's longstanding policies to promote energy efficiency certainly played a major role. But now we are entering a new phase where we must confront the larger environmental consequences of energy extraction, distribution, and consumption. California is committed to making another right-hand turn and begin now a downward march so that our absolute consumption of energy and our carbon emissions will be dramatically lower than today. We enter this phase, I think, with some fear that the economy cannot withstand such a wrenching transformation, and that it can only be accomplished through huge sacrifices. These fears resemble in many ways the discussions that occurred 30 years ago when that first right-hand turn began. So it makes sense to reflect on California's experiences. Can we use the past as a way of understanding the future? So the first Roots lecture focused on the origins of the key policies that made California uniquely energy efficient. Art Rosenfeld described how he and his colleagues first recognized how inefficiently Americans used energy, and then the collective size of the energy savings that he found and his colleagues found were enormous. And then Bob Foster described the origins of the Warren-Alquist Act in 1974, which introduced the minimum energy standards for buildings and appliances, along with the creation of the California Energy Commission to administer those programs. And then finally, Ralph Cavanagh spoke about devising policies that allowed utilities to profit from selling less energy. And the concept of decoupling was mostly born in California, but was certainly first field tested here. Then our discussants and the audience, many of whom were in the midst of the action and can recall some of the things that were happening 25 and 30 years ago, added color and I think some humor to the conversations and discussions that followed. Today, the discussion shifts to technologies, the roots of energy efficiency technologies. Not too long ago, when California took that right turn in electricity use, a curious asymmetry existed regarding energy. While the experts knew with considerable precision where our energy came from, they had little or no sense of how that energy was used, or that is to say, where it went. And they didn't know how much energy was going to lighting or heating or to televisions and all these other end uses. The consumption side of the energy equation was something of a black box, sometimes affected by fluctuations in the weather or the season, but basically something that could not be modified in any sort of way. And that ignorance of the consumption side has certainly influenced our choice of energy policies since then. And I'll give you a few examples of this difference in perspective. Let's consider the supply and demand for electricity. The slice on the chart shows the approximate amount of electricity supplied from hydroelectric sources, that is, from dams. By coincidence, this matches the electricity consumed by our nation's refrigerators. Now, with this information, we might want to consider the alternatives of building more dams or building more efficient refrigerators. If the electricity use of refrigerators could be halved, would this be more attractive than building more dams? Here's another example. Few people realize that over half of our electricity is consumed by electric motors. These motors are everywhere once you start looking for them. They are in refrigerators and air conditioners and water pumps and disk drives and fans, There are millions, if not billions, of them in our country. And the curious thing you'll see there is that motors consume more electricity than is generated by all the coal-fired power plants in the United States. So clearly, if we want to reduce electricity consumption and reduce carbon emissions, then we need to address motors and the services that they provide. Understanding the details of the demand side can provide other perspectives. Now, automobiles are very complex technologies, but we know that about 20% of the fuel consumption is used to overcome the rolling resistance of their tires. And that rolling resistance is the energy dissipated by the continuous flexing and reforming of those tires as they're spinning along as you drive along. For comparison, the oil consumption, that 20% of the oil consumption roughly corresponds to all of the oil that we import from Saudi Arabia. Now, recent technical improvements have made it possible to dramatically reduce a tire's rolling resistance, sometimes by as much as half, without sacrificing grip and tread life. So, from a policy perspective, should the United States invest more in increasing oil imports or reducing the rolling resistance in tires? Now, these examples illustrate the insights gained from a better understanding of the demand side of the energy equation. They also illustrate the potential impact of energy efficiency. As you will see, California again led the way in developing and promoting products with higher efficiencies. And today we selected 3 technologies to illustrate California's role: windows, refrigerators, and the compact fluorescent light. Now, we could have chosen other technologies that we think played an important role, but they weren't so visible to most of us. So we thought these would be, I think, closer to you as an audience. For example, one of the technologies we chose not to use and talk about was the concept of simulating the energy use of a building. And this technology and these procedures were pioneered in California. And this innovation has had global impact because without it, we'd be unable to design energy-efficient buildings. Unfortunately, computer programs and the algorithms aren't terribly sexy, so we spared you that history. California also invented the fuel economy test for automobiles. Now, measuring the miles per gallon of cars was not the original goal of this California test. It was actually to measure the tailpipe emissions from those cars. But it turned out that a simple side calculation from the emissions test yielded the fuel economy, or the miles per gallon. And so when the first oil embargo arrived, the federal government had a proven technique to measure fuel economy and a database of measurements for all those cars. And that allowed California to quickly establish that allowed Congress in the United States to quickly establish fuel economy standards for cars. In this way, one of the nation's most important efficiency policies can be traced to solving an environmental problem in California, that is, the smog in Los Angeles. So today, you will find that each speaker presents a perspective on the development of an energy-saving technology. As you listen, I hope you will reflect on how the researchers' stories contain the uncertainties and the doubts that we have today as we address that next right-hand turn. And in this way, I think we can learn from the past in order to shape the future. So let's move to the first speaker. And the first speaker is going to be Professor Michael Siminovitch. And there will be 2 discussants, Michael Niels from Niels Engineering and Tim Tutt from the California Energy Commission.
We live in interesting times in California, and I think this slide sort of reflects the kinds of thinking, the dialogue, the exchanges going on between industry, utilities and state institutions. It's a challenge, but I think we have tremendous opportunities for next generation technologies. And I think Jackie talked about that a little bit earlier, that the opportunities is in front of us. And I think we've just seen the tip of the iceberg in terms of energy efficiency opportunities. But we have a lot of issues to deal with. Why do we look at history of technologies? I think that we're at a very important juncture right now in terms of what's next. And looking at how we formed technologies, how we formed policies, looking backwards and trying to understand where were the successes and where were their problems, trying to really understand that kind of process allows us to be more critical and more insightful about shaping policy and developing technologies in the future. So I really look a lot to history in terms of allowing us to become more formative and more insightful in this decision-making process. I look at the whole process of change as being both market-driven and product-driven. And when I refer to market-driven, I'm really looking at how we address, as a culture, how do we address societal needs and user needs, and how do these things work together? And I think the compact fluorescent lamp is a really good example of where we have conflicting issues between user needs and societal needs, and we need to resolve those. The second issue is product-driven, and product-driven is when we develop a new technology or a new way of doing something, how can we apply that to solving user needs? So I look at these things that working synergistically. The theme that I've taken throughout this presentation is changes in product respond to need. And I think particularly in lighting, you can trace the way products evolve and how they've responded to need. And so I want you to keep that in your mind as a filter throughout the presentation. The history of light is really linked to its production. I think you can go back, and I teach this history of lighting class at Davis, where we really sort of drill into this to really get folks to understand, you know, how were light sources developed, how were they applied in spaces, and how does it shape our architecture and our spaces. And so really looking at this whole transfer of energy from, you know, potential energy to radiant energy, and looking at the process of how that's evolved over a long period of time allows us to really look at sort of future applications. Lighting has been by and large controlled combustion. I mean, this has been the primary source of light for us as a species. And until the 1800s, it's been almost the exclusive use of, or entirely exclusive use of burning hydrocarbons. And this is taking stored energy in biofluids and then converting it into some small amount of smoky radiant light inside of space. If you look at the whole form follows function, a lot of these early geometries for lighting systems inside buildings really formed, the form of these things classically followed the need. And there was to have something that contained a fluid, something that would be portable, something that have a certain aesthetic appeal to it. So this at a very basic level appealed to the direct needs of the end user. So the shape and the form of this was very responsive. Changes, again, in product responded to need. The ability to have portable lighting. I mean, this is sort of the first kinds of issues when you look at the evolution of lighting systems, that they're fundamentally responding to needs. Okay. Rush lamps in the 17th century, again, the need for portability and the fact that fluids were very expensive. So the average homeowner couldn't really afford to burn fluids in oil lamps, but they could afford to burn small pieces of rush that were dipped in tallow in order to be able to find their way. In the development in the early part of the 1800s, looking at whale oil. Whale oil had very high caloric value, and so people were able to have much brighter lighting systems and with a high degree of portability. So again, looking at both product and market-driven changes in lighting systems. Camphene lamps in the mid-1800s. This was a fluid which had a very high caloric value, so people were able to have very bright little lighting systems. And again, responding to both the product and the market-driven change. The electric lighting era looked at the concept of a different form of transfer of energy. And this was basically arc lamps and filament lamps and today's discharge lamps. And this was made possible to us by the ability to both generate electricity and also store it. And early work by Volta allowed this potential energy to exist so that folks could develop products and technologies using this as the base. Very early work by Davy was some of the first carbon arc lamps, taking this potential energy and actually being able to use it practically for the lighting of spaces. Again, this was a user-driven need, but it was made available through the product development of stored and generated electricity. Early carbon arc lamps exploited this potential energy for useful lighting of exteriors. Also during that time, Faraday was experimenting with discharges. Again, he was not looking at light sources. He was in a laboratory as a scientist developing the science behind discharges, not with the purpose of generating light sources. It was later on that this advance was used in a practical sense as a market-driven activity. Glow discharges essentially form the basis of most of our lighting systems today, and it was based on this sort of product development work that was not user-driven. Again, mid-1800s, significant levels of oil production, and this was actually something in which we looked at wide universal access to lighting systems. And with lots of oil being available, significant oil production, people were able to have light inside their spaces cheaply. This was a very inexpensive fluid, had good caloric value, and again, changes in product respond to need. People needed a lighting system. There was available of cheap energy, very portable, and allowed lighting to go into many spaces. Again, we're looking at the way light shapes buildings, and daylighting is again the primary source here. Kerosene was incidental in the early phases. The architecture of this building is very much formed by daylighting. Gas lighting started to not just having portable fixtures, but actually hardwired fixtures in which there was plumbing to each one of the sources, which would allow a distribution of gas to individual light points. The next phase was getting into the early Edison lamps, and again, a number of folks developing this kind of technology, but again, it was both a product development and a user need driving this. Okay. Early electric lighting, and again, this really starts to get into the whole issue of compact fluorescent. Typically low wattage and very expensive electricity resulted in light sources in very close proximity to the task. You could call this a very early form of task ambient lighting system, which is now becoming vogue for our commercial buildings. But again, very low wattage, very expensive electricity, used very judiciously. Okay. And you can actually see here that very early electric lighting, sources mounted close to the ceiling, people all huddling close to the daylight, and this is what you call an ideal daylighting design. They've turned off all the electric lights because they have daylight. But again, early electrical fixtures, small lumen packages. Okay? And this sort of gets right into the very early phases of compact fluorescent. As a product-driven activity, as electricity became cheaper and the light sources got bigger, it allowed us to abandon daylight. And again, I don't say that in a positive way, but there was a lot of forces here in which large open spaces, construction became cheaper. They were able to have lots of people working in company format in large open areas with the availability of large light sources and inexpensive electricity. So this is very much a product-driven activity. 40s, windowless offices with surface-mounted fixtures. And again, I trace this back to the first genesis of the compact fluorescent lamp, understanding these are all incandescent light sources. Okay? So this type of geometry offered tremendous flexibility in terms of commercial building development, allowed people to sit anywhere inside a space. People are essentially abandoning windows. The fixtures were small, surface-mounted fixtures, and this was really the genesis of the compact fluorescent lamp. Now I'm going to go back a little bit in terms of looking at low-pressure discharge light sources, again, fluorescent lighting systems. There was a lot of work done by this individual, Heinrich Geisler, looking at low-pressure discharge light sources, but predominantly as an art form. He wasn't doing it pursuing a need in terms of looking at practical use of this, what he was doing was exploring the use of small discharge light sources as an art form, and was developing very complicated low-pressure discharge light sources as an art form. And these were coiled pieces of glass filled with different types of gases that glowed when you put a potential across it, then drawing on previous work. Some of these things were quite beautiful and quite ornate. Again, they were a decoration light source. And you can sort of see the whole evolution of coil lamps today, the compact fluorescent lamps, can actually be traced back to the 1850s in terms of some of the work that they were doing with these glass tubes. There was a considerable amount of work taking this and trying to reduce it as a market-driven activity. How can we use discharge light sources for the actual lighting of interiors? And so the patents on this go back into the 1920s, looking at fluorescent light sources. Fluorescent light sources practically started entering the marketplace in the 30s. And this is kind of an interesting slide in which they're putting tons of fluorescent lighting in. They've papered up all the windows here, complete denial of daylighting, because now they've got a very cheap available source, fluorescent. So fluorescent lamps had a significant impact on the way we build and operate buildings. It was cheap, inexpensive, made in large volumes, lots of light, a long life. So we're all familiar with this. How this fits in with compact fluorescent in terms of, I wanted to give a little bit of the background in terms of market and product driven, but fluorescent technology really looks at both these sort of technical developments with market drivers. And I'm going to trace a little bit on this in terms of key technology attributes for fluorescent. And some of the very, very first patents on fluorescent were these sort of U-shaped lamps, and this goes back to the 20s, and the patent literature is very rich, but this was one of the central patents from Germer, very early work. But what's interesting, if you look at some of the very early technologies and look at what we're doing today with U-bend or compact fluorescent lamps, there's not a great deal of difference here, okay? So it's almost 100 years in terms of separation on this thing. These are essentially compact fluorescent. These are pre-compact fluorescent lamps or U-bend lamps, and this is one of the first fluorescents. So these things are not greatly different. In the 40s, we were building spaces with incandescent lamps, and these were surface mount fixtures. There was tremendous stress here to have smaller volume light sources and increased lumen packages, and linear fluorescent wasn't fitting into this. And this was a patent that actually I found of some early fixture development for offices. This is the first reference that I found, and you can actually see compact fluorescent. Figure 12 refers to a circle line lamp, which is one of the earliest gestures towards compact fluorescent. And the patent literature is rich on this. And again, the pursuit on this was market-driven. Small lumen packages designed to go into small fixtures because we were using incandescent lamps. Okay. So much of the early, what I call sort of the initial compact fluorescent, was really driven from the circle line lamp. Yeah. I found this was interesting. This was one of the early, what I call modern compact fluorescent lamps. This was 1981. And if you look at the original, one of the original patents on fluorescent technology, there's not a great deal of difference between these two. Okay? The only difference is we put an Edison base on this. In this case, there's no reference to a base. And this is very much market-driven. We need to have this type of lamp, and we need to have this type of socket in order to fit into a socket. Okay. So I looked at circle line lamps as what I call first-generation compact fluorescent. But they were highly constrained in terms of lumen output and color, and that has to do with the white phosphor that's covering the inside of the lamp. The white phosphor inside this lamp, as the lamps get smaller and smaller, there's proportionally more lamp loading. And so with this increased lamp loading on the phosphors, the lamps didn't last very long. So there was tremendous pressure to be able to take a lamp like this and move it to something like this, smaller, that would fit into smaller spaces, but we didn't have the phosphors. So there was a tremendous amount of technical work that went on in the 60s and 70s to address the issue as these lamps get smaller, we needed to have a phosphor that would be able to stand up to the increased power density. And so inside a fluorescent lamp, there's a UV discharge. This UV discharge excites the white phosphor. The white phosphor re-emits in the visible spectrum. As these lamps get smaller and smaller, there's proportionally more loading on the phosphor. Smaller lamps don't last long. So tremendous pressure to develop better phosphor. It's been said that the successful development of the CFL is almost entirely due to the development of new phosphors, and I think that's true. The new phosphors that were developed were able to stand the increased loading, and that made the possibility of high-performance phosphors that would last a long time. So what I'm referring to here is the concept of narrowband phosphors, and the narrowband phosphors in the blue, green, and red allowed enough light to give you approximately 80 CRI, color rendering index, was able to stand the wall loading, and was able to last a long time. So this was a significant technical achievement that allowed compact fluorescent to go to the next step. So we went from circle lines to next generation lamps. And I'm going to show you two challenges on this. First one was very early screw-based fluorescence, and this, again, used the enhanced phosphors inside the lamp, used the magnetic ballast, was lasting about 5,000 hours. And this is in 1983, and it was one of the first real Edison-based compact fluorescent. Electronic ballast came along soon after that to address issues of both weight and instant on. And again, very much a market-driven activity where users were saying, our lamps are falling over because of the weight, and I'm also dissatisfied with the flickering. So this drove the electronic ballast. Okay. Actually, one of the first coil lamps was developed by Ed Hammer at GE, but it took about 10 years actually for this to actually get into the marketplace because there were many other compact fluorescent lamps. This was initially ignored by the industry. Okay. Market drivers. There were very significant market drivers, and then again, it happened here in California. I think the oil embargo was a national phenomenon, but California actually listened and said, "Hey, we're going to do something here." We're all familiar with this famous curve. The key market pushes for the CFL in terms of sort of being market-driven operators that worked on our technical enhancements was lots happening in the Title 24 activities of the late 70s. It was really the rebate programs in the early to mid-80s that drove sort of the first penetration of compact fluorescence. We saw the power densities bringing up the T8s and the trichromatic phosphors, but it was really the rebate programs in the 80s that drove the first generation of the CFLs. There's a second phase of activities that's happened with CFLs, and I'm going to get into that and that's the large federal-based procurement programs that said, look, we need to drive the cost out of these things. Some residential programs, and then some really good code activities. And again, we're familiar with this process, which took our commercial office lighting from 4 watts per square foot down to 2.5 watts per square foot. And it was in this whole generation here that T8s and trichromatic phosphors and electronic ballast really happened. Okay. The really big point for history for compact fluorescent, the big driver on this was incandescent downlights. And incandescent downlights, in my opinion, really started the revolution for CFLs in this state. And in the 70s and 80s, one of the largest numbers of fixtures sold was recessed downlights. And you see them all over the place here. There's lots of examples. And basically, they used various flavors of these heaters. This is an R lamp, and it's about either 10 to 12 lumens per watt, depending upon the flavor. But 60 to 100 watts was the typical lamp in this. And again, this was, in my opinion, the big driver for compact fluorescence. It really made the difference on this. And some of the initial rebate programs that came up really made this happen. And it was basically taking a 13-watt twin tube, this type of compact fluorescent lamp, and replacing this with this type of fixture. And this is, again, has the same kind of form factor, but this was 13 watts, and this was 60 to 100 watts. So there was some very insightful rebate programs that really pushed this. And again, with a 100-watt system, we're looking at a 1-year payback with some of these rebates. Okay. So this thing ended up to be, this technology was one of the first real practical applications that took this technology forward. And the largest user in the country of compact fluorescent lamps was here in California, making this type of geometry. Okay, so this was really the first, it was magnetic valves, it was small geometry, and again, it was one of the first big pushes on this. Again, this technology was very popular before the rebates started going away until we got more standardized code. So in the late to early 90s, there was a secondary shift that moved into what I call dedicated fixtures. And these are fixtures that were designed explicitly for fluorescent. There was a corresponding reduction in rebates, and manufacturers started really getting into dedicated fixtures. Now, this is a small point here, but an important one. In terms of the calculation of power density, UL, the Underwriters Laboratory, became the standard. The rated wattage became the baseline for calculation, and that was an important issue. So dedicated fixtures are basically fixtures that leave the factory designed for fluorescent, and that was really very code-driven here in California. So there was a big shift away from this type of technology into this type of technology. Again, combination of integrating electronic ballasts and compact fluorescence, but very much market-driven. Okay. Residential programs, really the big drive in residential that occurred here in California were affected by large national efforts to reduce costs. And this was very large procurement efforts that were designed to say, let's bring the cost of these things from $20 down to some lower cost. So there was a lot of effort going in on a national level to drive cost. Also the utility upstream programs that addressed the CPUC goals, and then the dedicated code change in California. Title 2405 was probably one of the largest single changes in compact fluorescent technology ever. And this is where, if you go into a typical California home today, it's built according to 05, over 50% of the light points are fluorescent. So it's been a major success story. The kitchen is required 50% to be high efficiency. So this was a huge signal to the industry that California was indeed serious, and it really spawned a very large growth in compact fluorescent. Title 24 has been hugely successful for new construction. And again, we've gone out and we've done surveys with our builder partners, and almost 60% of the light points in the home are fluorescent. And these are dedicated products. Okay, so this was a huge success story. But again, this huge success story here of the 50% is only being applied to a small, thin slice here. And what we really need to be doing is going after all these other 80% of the homes that are still using heaters. Okay? So the challenges are really in this area, and this is where I think we're at now today. And this is, again, market and product driven. The road to Huffman, we're looking at 50% goals here. And this is going to be a game changer in terms of how we light spaces. And everything we're doing in our homes we're going to have to be doing things differently to get there. The national programs have driven out the costs. Okay, so we're down in the $2 per lamp. And when we were starting this, we were up at $14, $15, $20 a lamp. Well, now we're down in this region here. And certainly we're selling an awful lot more lamps here in California. It's been a big growth curve. But we're still married to this technology. Okay? We're still married to heaters for providing our light sources inside our spaces. When you go into these kinds of showrooms, you will not find these types of lamps. And if you ask them, they say, oh yeah, we have some in the back room, we'll show you. But by and large, they're still using heaters for these types of applications. When we looked at this hard, we worked with our industry partners, and in 2007, we had a 15% market penetration in residential of compact fluorescent. And that's dismal if you think of the amount of time, energy, money that we spent. We have recent data that says that today it's up to about 20%. We're moving in the right direction, but if you look, we're still in the more than 50% of the light points in the home are heaters. Something needs to be done. So the current issues and sort of the takeaway on this is that there's unanticipated consequences with any kind of technology development, and unanticipated consequences are things that happen that you didn't expect. And the other one is unfulfilled consumer expectations, things that didn't happen that you wanted. So I want you to think about that for a moment in terms of this. And again, I didn't say this, but some people think I did. Light bulbs that make your entire family look like cadavers, 5 of the 6 bulbs dead in less than 2 years, and I'm waiting for LEDs as the savior for this. And so this is some of the dialogue that's going on in there. The issue is incandescent lamps have very well-defined performance and expectations. They do things that we know, okay, and that some people like. CFLs are typically a departure. Now, the departure can be very small or it can be very large, okay? And the departure is typically in color, dimming, and longevity. I'm not going to go through this, but basically, Young-Helmholtz color theory is we're looking at 3 broad color sensitivities of your eye, and most lamps appeal directly to them. So we have these 3 broad color sensors in our eyes. And daylight's a very broad spectrum, as is incandescent. And so we're taking 3 pieces of that and coming up with a CRI of 80. Now, when I was a grad student some few short years ago, I was sitting in a room when they were deciding on some of these issues as an invited student, and I was sitting way at the back, and I was listening to the discussion on what is going to be the standard for CRI, and the standards came up that 80 will be just fine, and 80 is relative to daylight or incandescent, and incandescent and daylight are typically 100. And 80 was said, that's going to be okay, because you know something, no one's ever going to use fluorescent in the home anyway. Now, I'm sitting as a graduate student in the back of the classroom, I don't know, that doesn't sound quite right to me. So now we're dealing with these issues. Also, to tease you a little bit, this is just a little bit of demographic information. And what I looked at here is if you look at married households, 51%, female households, 12%. So about 60% of the households, there's a lady involved in the decision-making process, if not owning the decision-making process. But interestingly enough, recent data is showing that 15 to 40% of women may be tetrachromats. And what that means is instead of having 3 sensors in their eye, they have 4 sensors in their eye, and they have much better color appreciation than we do as males. Okay? Makes you think. Okay. Also, 2007 survey, there's about 10 dimmers per home. 90% of the incandescent high-watt fixtures are on dimmers. And unfortunately, these things don't dim as sweetly as these do. Okay? When you dim an incandescent, it's very predictive. You know what you're going to get. When you dim this, you've got multiple choices. Okay? And that's an issue. I didn't write this. This came from a utility out east. When CFLs fail, they may emit smoke, an odor, or popping sound, and for immediate release. And this is not a good testimony to a new technology, and we need to address this. So, changes in product, I asked you to remember this, changes in product respond to need. And the question here is whose need? And what we really need to do is drill into end user needs, because we've had government agencies and utilities look at cost and efficacy on this thing. We should be looking at amenity and quality. Programs, CFL programs that address cost and efficiency, when we've done this for a lot of years now, we end up with 50% of the sockets still being incandescent because we've not fulfilled things like quality, color, and amenity, and we need to group on that. I'm proposing that if we're down in the $2 per lamp region, we can afford to invest $1 of that into a CFL that dims sweetly and has amazing color. I spoke to the vice president of the largest lamp company on the planet, who said, we can make this any CRI you want. We can make this look like this. It's just a matter of cost. So I think that in the pursuit of this low cost, we've driven out some of the quality on this. Come on. Hoffman Bill. Hoffman Bill is important. If we do nothing from today on, we're not going to get the 50%. If we put all light points in the home at 40 lumens per watt, I don't think it's about efficacy. We've got good light sources at 40 lumens per watt. If we converted all our light points in the home to 40 lumens per watt, we would get there. We would get the 50% savings. So, to finish up, changes in product respond to need. And what we've developed here is a collective with the utilities to look at the opportunity of what we call super CFLs. And super CFLs are lamp technologies that will have great color, will have very long life, and will dim easily. This is a pre-CFL. This has an 85 CRI, okay, 85 CRI, with the opportunity of moving that to 90. It has very enhanced reds. In other words, when you go into a mirror and look in a mirror, you need to look good, and its skin tone is rendered by red. It also will last a very long time and will put up with the heat inside downlights. And so this isn't quite commercially available yet, but industry can respond to this, and they can make a technology that's like this. So this is what we're doing here in California. So I think I've run out of time.
What's interesting is that with any technology, basically what is necessary is for the industry to embrace the technology and accept it as a viable option. So I was in Amsterdam in 1983 at the quadrennial of the International Commission on Illumination, the CIE, and I'm out there in Amsterdam and I'm looking at this post-op luminaire and I see this compact fluorescent lamp in there. You know, it was a Philips lamp. It was a little PL9 or something like that. And I'm saying, my, that's interesting. Here, fluorescent has a problem with starting in cold temperatures, and Amsterdam gets cold, and it kind of shook, it kind of turned my head a little bit and said, well, maybe I ought to look into this. So my brother builds a house, you know, in the local area here, and he says, I want efficient products in my house. So I found 2 California manufacturers, well made, for an outdoor lighting product that had a Panasonic lamp in it, and Prescolite that basically had a indoor downlight, and we put those into his house in 1983. They're still there and operating. So there's just a little bit of an anecdotal information about the utility of this product. In the mid 80s, what I engaged in is basically a change in the lighting design practice that we performed, and looked at the task ambient opportunities that were presented with compact fluorescent lamps. Now we had an opportunity to put ceiling mounted luminaires, linear fluorescent lamps around the task, and then in other areas of the room, say the wall or the seating area for guests in an office, we could use some downlights or some wall washers and basically create an environment where we didn't need to have the power densities that we would have had if we were using all linear fluorescent lamps. So from that standpoint, I started to understand that there's many more opportunities for this product, and it was just a matter for the industry to really catch up and develop the types of luminaires that were necessary for our use. And what was happening is that not only in the commercial sector, but also in the industrial sector, the compact fluorescent lamps started to become more prevalent. In hazardous locations, the prevalent lamp use was for Class 1, Division 2, Class 2, Division 1, you know, in basically vapor locations, you know, like a Chevron refinery, for example. You would have these lamps on the catwalks, basically, that were all incandescent, you know, in a bulb, basically, you know, a globe that would essentially seal out the gases, and those were incandescent. But with the compact fluorescent lamp, those types of luminaires now could become more efficient, longer life. And then towards the end of the 80s, really what happened was that we now had the electronic ballast that was available to us, which did provide that dimming capability and also a much more efficient system. And as Michael pointed out, the real key to these lamps is that the improved color. And this is a kind of a trend that's developing. Early 90s, here's another piece of anecdotal information. I got a call from energy efficiency people over at SMUD, the local utility, and they said, well, what do you think about this, Mike? You know, we're going to offer about $150 a kW for, you know, compact fluorescent lamps that owners would put into their facility. Well, I said, you know, I'm really not sure about that, because, you know, it's going to cost anywhere from, you know, $75 to $100 per luminaire to install these, and this is not a retrofit screw-in solution. This is basically changing out the luminaires. And maybe the savings are going to be something like 40 watts perhaps, if you take an incandescent downlight out of service. And you add that all up, and it's a very expensive proposition, so it wasn't going to be something that the typical customer was going to be very interested in. Lo and behold, in the mid-90s, SMUD at one point was paying for 100% of the lighting retrofits. And the reason they were doing that was because they were looking for generation through the efficiency. They were able to buy this by doing lighting retrofits of all different types, including the use of compact fluorescent lamps. In the last decade, as Michael's slide showed, the use of compact fluorescent lamps has really become ubiquitous. And what's interesting is that even though there's been this great increase in the purchase of those and the installation of those lamps, there's still a great opportunity to use them for these applications where we need smaller lumen packages and we need to do defined sorts of lighting jobs. And what we're finding is that we really have more choices in terms of wattages, shapes, color, and that's really the opportunity that's ahead of us with respect to that lamp. It's been in place now as I said, in these facilities, commercial industrial facilities for over 25 years. And it's getting penetration in the residential market primarily because of the incentives that the utilities have provided. Friends are now putting these lamps in their houses because they realize, hey, if we put these in our house, what we're going to be able to do is reduce our electricity bill. And that is becoming more important to people as they are looking at their budgets and what they have to spend on energy versus what they would spend on, say, going out to a movie or perhaps a restaurant. It's becoming a bigger part of the individual person's budget. So I guess in closing, I would say that it's really good to see in this group that there are some people that don't have gray hair. And you'll find that the people that are talking about these things that have occurred in the past, are still the same people that were there doing it, and they're still doing it. David Goldstein, Steve Selkowitz. These are the people that have been doing it for years, and we need new people to help get past this awareness level. We really haven't gotten past the awareness level, and that's kind of the challenge that we all have, is to get people past that awareness level to the level where they can make an informed decision about what they're doing in terms of using energy.
I was actually fascinated by Michael's history of lighting. It reminded me that when I moved to Sacramento in about 1990 and bought a house that was built in 1924, I couldn't figure out why there was a gas pipe in my attic. And then I happened to put a little bit of weight on it at one point, and I noticed that something had poked through the ceiling in my living room right in the middle, and I figured out it was a hardwired gas lighting system that had been capped off long ago. And we've changed, obviously, quite a bit since then. The world had moved to the incandescent, ubiquitous incandescent light bulb of 40, 60, 75, and 100 watts. That we all were familiar with, but I don't know if you've noticed, but in California today, it's really difficult to find one of those 40, 75, 100-watt bulbs today. And you go out to the store, and having worked on energy efficiency and lighting, it's one of my habits. As when I go to the grocery store, to a new store, I almost always tell my wife, I'm going to go check out the lighting aisle and see what's going on. And I do go over there, and you see now 57-watt and 71-watt bulbs, along with a whole bunch more compact fluorescents and other choices that you have. And so change has happened, and it's going to continue to happen. I mean, I know that we've looked at what's been happening in the last 10 years in California, and Awareness of compact fluorescents has increased from 60% to 100%. We're at that awareness level now. People know what they are. Purchases have increased from 17% of households to 77% of households have at least tried these compact fluorescents, and 80% of households today are using at least one. There's still that 20% out there that hasn't jumped onto this revolution. And people seem to be generally satisfied with the CFLs that they have are using, although I do agree that some improvement in quality would be useful. And I want to mention as well, keying off what Michael said, I don't think it's just a cost that might suffer a little bit with that increase in quality, but there might be we might have to accept a little bit less efficacy to get that increase in quality. As you get into these red phosphors, it's my understanding anyway that it reduces the efficacy of the CFL a little bit. It makes it a little bit harder to achieve the highest efficacy bulbs out there. There's been a tenfold increase in CFL sales in the last year, from 1 million a year to 11 million a year in California, and a 70% drop in the same period in incandescent bulb sales. So today, or last year in 2000, I think this is 2007 data actually, it seemed like 25% of the sales were CFLs as opposed to incandescents. And to some point, that is a market transformation. I know that in the Pacific Northwest, they stopped incentivizing regular CFLs because at 20% of sales level, because they figured that with the longevity of CFLs, that 20% per year sales would eventually fill most of the sockets that would be useful for CFLs. And in many cases then people are shifting to trying to address specialty lamps. As many as 50% of the sockets in a home are specialty lamps. They're the globe lamps in your bathroom. They're the downlights fixtures that are becoming more and more ubiquitous. The smaller base candelabra kind of lamps. So moving into getting high efficacy bulbs in those kind of fixtures might be the next way to go. A slight story, in one of my lighting trip aisles, I went to a store and I noticed a package of 2 dimmable compact fluorescents, and they were on some kind of special, maybe an upstream special from PG&E or something, but the sign said 3 for $1. And I didn't quite understand that. Here's a package of 2 bulbs, and the sign says 3 for $1, and I couldn't figure out whether it was 3 packages for $1 or 3 bulbs, but they only come in 2. So, I had to buy one, and sure enough, these bulbs were 33 cents each, but for some reason they came in a package of 2, and 3 for $1. One of the ways that we have achieved and cemented this market transformation, and Michael talked about it, is through standards. At the Energy Commission, we do appliance and building standards, and Michael mentioned the building standards requirements in Title 24 for new homes built from 2005 on are very significant. 50% of the wattage in kitchens have to be high efficacy, which basically means fluorescent today. We also have developed appliance standards for those general service bulbs, and that's one reason why, as I said, if you go to the store, you can't buy a 75-watt bulb very easily or a 60-watt bulb very easily, an incandescent in California today. And we developed and adopted standards that required, it didn't ban those kind of wattages, but it made it easier for companies to meet the standards if they reduce the wattages of those of their standard bulbs a little bit. And they all have been doing that, all the major manufacturers. I mean, there's still some of those older bulbs that you can find, but today it's mostly the slightly reduced wattage, slightly 5% energy savings that you get from those that you can get out there on the market today in California. The federal government and around the world, of course, have been looking at addressing these, and the federal government in 2007 passed a law that required a much more significant reduction in wattages for these incandescents, as much as 25–30%, which we all don't think can be met with a standard incandescent technology. The lighting companies are going to have to go to a halogen infrared coating technology that's going to cost significantly more and further drive the comparison by the consumer to CFLs to what they normally would buy into perhaps more purchases of CFLs or more ready purchases of CFLs. In addition, that federal law requires moving to approximately 45 lumens a watt by 2020, and here in California we've accelerated that to 2018. This is one of the ways we're contributing to the goals in Hoffman by moving by 2018 to that high level of efficacy for general service lamps in California. Another thing that we did and adopted just last year was to adopt standards for portable lamps, the kind of table or floor lamps that you plug in. And I mean, generally, people might have used incandescents in these. What we did was we said, if you go out and buy one of these in California, this happens starting next year, the manufacturer has to package something like a compact fluorescent to fit that socket that he's selling you in the lamp. Maybe there's two sockets, he has to put in two. And effectively, then, we're hoping and believing that the consumer will have this readily available when they plug in the lamp, they'll screw it in, or if they don't want it there, they'll screw it in somewhere else in their house and move more into compact fluorescence. I mentioned the building standards. I'm just going to tell you another story that relates to some of the quality issues with compact fluorescents. I recently visited my in-laws up in Eureka, and they had just built a brand new, fairly significant house up there. And I walked through it for the first time after it had been done, and there's not a fluorescent light in the house. And I said, how did you get around the Title 24 lighting requirements? And my sister-in-law said, medical exemption. And they do have a challenged child who is subject to seizures, and she said that fluorescent lights give him seizures. Now, I've heard of this, but I don't think there's any peer-reviewed scientific studies that verifies that there are seizures from fluorescent lights. And two, there's absolutely no medical exemption for this in Title 24. But that brings us to enforcement. Building departments around the state can be convinced that there are reasons not to follow the standards, or maybe they just are not aware of them. In some ways, we have to increase our enforcement activity to be able to make sure that we get the savings that we're looking for from our standards. So I'll just finish up with a concept about what we mean by market transformation of CFLs. I mean, as I said, in the Pacific Northwest, they talk about if you're getting 20% of the sales, then that's going to penetrate the sockets, and the market is transformed. And what I would like to see is a market where when the consumer goes to the store, they're not thinking, can I use a CFL in my closet, or is that not a good place for it? Can I use a CFL in my kitchen, or is that not a good place for it? They're looking to buy CFLs because that's what they're used to buying. That their new rule of thumb is they're out there buying CFLs, and they're installing them, even if it's in a place where cost effectiveness may be challenged because they don't turn it on very often. But they're still buying CFLs because that's the new rule of thumb. And I kind of equate that to a degree to the lighting market in Japan, where they're way beyond what we would be talking about with a CFL residential lighting structure here, because residential lighting in Japan is predominantly linear fluorescent, which is much more efficacious than compact fluorescence. and the people there are just used to it, and that's what they do. So that would be another way of doing market transformation. I'll end there.
Michael, if you want to respond to some of these comments.
I mean, I think this is some really great comments on this, and I wanted to add in a couple of additional insights relative to that to build on some of the questions. And one of the things is that if we look at the whole issue of enforcement, or we look at issues of what do we do in code structures and in standards to encourage folks, I think that we also need to look to our industry folks to respond to customer needs. And a person should go into a grocery store and purchase a compact fluorescent lamp because it's a better light source than what they've previously been using, not just because it's energy efficient. And I think that when we get the light source that has got brilliant color, can dim really nicely, will last forever, we won't need to enforce this. It will be people want to do this. And I mean, a really good way to sort of reflect on this is that we really need to be doing things differently. And I think we really need to look at what are the next steps in order for both the regulatory side and the industry side to work together to sort of make things happen and use some of the leadership that's going on the codes and standards. And I'll ask a very simple question, and that is, how many folks here have incandescent light sources in their mirror bathroom application, in the mirror bathroom? How many? How many have compact fluorescent in their mirror bathroom application? Okay. So it's 50-50. Okay.
You missed linear fluorescent.
Yeah, linear fluorescent. The other interesting thing is that there's other parts of the world that, as Tim said, have engaged in lots of this activity and are way ahead of us. If you go into a typical apartment type of residence in, say, Korea, you'll find 70 to 80 CRI light sources in the 5,000 to 65 Kelvin color temperature range. And if we did that here in America, in our homes with linear fluorescent, people would just get up and leave. They'd just get up and leave. And I was amazed in my first trip there that every single residence and home has got 70 to 80 CRI fluorescent lamps. And in addition, they're typically exposed fluorescent. Just a linear fluorescent, fully exposed. Go.
Thank you. Michael Siminovitch, Tim Tutt, Michael Neal, thank you very much for your contribution today.